Hear me? Good evening, everyone. I am Srishanta. I am a PhD student associated with the Center for Systems and Control at IIT Bombay, and I'm also the TA for this course, W46 Linear Dynamical System. So, welcome to 6-week tutorial session. So, let's begin. Write down the topics which we are going to cover today. First one is the concept of cyclic matrices. Then it's the state feedback. For multi-input, multi-output systems. And then we look at LQR. So this is using the concept from cyclic matrices. All right, so let's begin. A equals 1, 3 minus 2, 0, 4 minus 2, 0, 3 minus 1. So we have to determine whether the matrix A is cyclic. If A is Herbert's or not. All right, so let's begin. So first, recall the definition of cyclic matrices. So let's say a matrix. We will rename this A. So cyclic. If and only if the geometric multiplicity of each of its n eigenvalues is 1 or equivalently, if and only if n eigenvalues of the matrix A are exactly of its minimal polynomial. Geometric multiplicity or Gn fraction of the space of an eigenvector, eigenvalue. So let's see. So when lambda is an eigenvalue of the matrix A, then corresponding to each eigenvalue, there's a null space. Then each v not equal to 0, the space of K, which is or V such that E minus lambda V sorry, minus lambda I applied to V 0. Know that this is an eigenvector corresponding to lambda. For each eigenvalue, we have a space NA which contains all the eigenvector corresponding to lambda. The dimension of this subspace NA the subspace of what? So for A in Rn cross N, it's a subspace of Rn. So the subspace Na is called the geometric multiplicity of lambda. Let's first find out what the characteristic polynomial for the matrix A is. I. So let's calculate this. Let's see the matrix once more. Alright, so we have 1 minus lambda, 2 minus lambda, minus 1 minus lambda. You can see that this is an upper triangular matrix, so the determinant is simple. It's 1 minus lambda times 4 minus lambda minus 1 minus lambda plus 6. Okay, so let's expand this quickly. Okay, so this is minus 4 plus lambda minus 4 lambda. Oh, sorry. Just a second. So it's minus 4 lambda plus lambda plus lambda square plus 6. This is lambda square minus 3 lambda plus 2. So this is, you can find this out. 1 minus lambda, lambda minus 2, lambda minus 1. So the eigenvalues are 1, just a second, 2. So implies that the matrix is not Hermit's. Let's check if this is correct. It's 2 lambda minus 1. This is lambda square minus lambda minus 2 lambda. That's true. Alright. So the matrix is not Herbert's. Now let's consider the minimal polynomials. Alright, something like 2 minus lambda. This becomes 2 minus 3 lambda plus lambda square. And if we substitute a in it, we get a square minus 3a plus 2y. That the roots of the minimal polynomial. One and two, and eigenvalues of A are 1, 2, and 1. Therefore, we can say that the n eigenvalues of A are not exactly the roots of its minimal polynomial, which implies that the matrix is not cyclic. Some more questions on cyclic matrices. Then 1, 3 minus 2, 2, 3 minus 1, cycle. So again, let's find out the characteristic polynomial first, so we can control the eigenvalue values. So this is determinant of 1 minus lambda, 1 minus lambda, minus 1 minus lambda. Just a second. So it's the same question. Okay, so what we'll do is using the concept of geometric multiplicity. Okay, so we have seen the approach using minimal polynomial. Now we'll see how to test whether the matrix is cyclic or not using geometric multiplicity of the eigenvalues. Alright, so then we know that this is 3 minus 2 minus 2 is divisible by 3, 0, which is nothing but 1 minus lambda square, 2 minus lambda equals 0. So the eigenvalues are 1, 1, and 2. Okay. So for lambda equals 2, It just appears once as an eigenvalue, so its algebraic multiplicity is 1, which implies that geometric multiplicity is going to be 1 as well. The geometric multiplicity is also 1. For lambda equals 1, algebraic multiplicity is 2. And now we have to figure out the geometric multiplicity for this eigenvalue. Okay. So what's the geometric multiplicity? It's the dimension of the subspace, right? Or B in R3 such that A minus lambda I. So let's put lambda equals 1 equals 0. So by dimension we mean geometric multiplicity is the dimension of this subspace, which is the number of linearly independent vectors in the subspace N, which lies in R3. Now we'll apply the rank relative theorem. At the dimension of kernel of the matrix A plus dimension of range of A plus N, where A is in Rn equals, and this is exactly equals to rank of the matrix A. Okay, so now we want to figure out the dimension of A minus lambda. So let's find out the rank of A minus lambda first. The 1 minus 1 is 0, then 3, 2, 0, 0, 3, 3, minus 2, minus 2. Okay. Let's figure out the number of linearly independent eigenvectors in NA. So this should be applied to some eigenvector v1, v2, v2, v3 corresponding to lambda equals 1, 0. Equation is 3v2 minus 2v3 equals 0, which implies for v2 by 3 equals, sorry, v2 by 2 equals v3 by 3. And since v1 is not present in the equation, v1 can be any real number. So one of the eigenvectors is therefore let's assume that v1 equals 1. So the eigenvector for lambda equals 1 is 1, 2, and 3. Back to the rank of A minus I. Columns are there. So oh, it's just 1, right? Because Column 2 is simply minus 3 by 2 times column 3. One linearly independent. So according to the rank nullity theorem, therefore the dimension of the space in A is 3 minus 1 versus 2. So this is the geometric multiplicity. And because the geometric multiplicity is not 1, this implies again that the matrix A is not cyclic, which we have also found out using the minimal polynomial. Was clear to you. Now let's move on to the next question. So determine whether the matrix equals 2, 1 minus 2, 0, 2 minus 1, 0, 0, 1. Again, so we need the eigenvalues first. Determine of A minus lambda I equals 0, which is 2 minus lambda, 2 minus lambda, 1 minus lambda, zeros, 1 minus 2 minus 1 equals 0. So this is an upper triangular matrix, so the determinant is easy. This is simply 2 minus lambda, again 2 minus lambda, and 1 minus lambda equals 0. This implies that lambda equals 1 and 2 repeated eigenvalues are 2. So again, the matrix is not herpes because the eigenvalues are positive real part. One, which simply implies that GM is 1. Now, for lambda equals 2, let's find the rank of the matrix A minus 2, which is the rank of 0, 0, minus 3, 0, 1, minus 2, minus 1. So we can see that there are two linearly independent rows, this one and this one. Check. Or since the square matrix, we can just eliminate that the rank is not 3. So this is 0 times 0 minus 1 times not 3. That is two rows which are highlighted are linearly independent. So let's check quickly. The third equation would imply that alpha q is 0. First equation is just 0. The second is alpha 1 equals 0. Then the third one is are linearly independent. Therefore, rank is 2. Therefore, according to the rank-Halley theorem, that the dimension of null space of A for lambda equals 3 minus 2. This is the geometric multiplicity. The matrix A is cyclic. This question was clear to you. Now let's move on to the next one. So in the next question, we are going to determine whether the matrix is cyclic or not using the concept of Jordan normal form. So let's just recall first. So this is the next question. So the matrix its element A is called cyclic whenever the Jordan form of A is one Jordan block associated with each distinct eigenvalue. Just a second. So let's move on to question 4. So it's 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1. And the other one is -1 -1 0, 0 -1 0, 0 0 -2. Whether these are cyclic or not. Okay, so let's first find out for the first matrix. So A is 1 1 0 0, 0 1 1 0, 0 0 1 0, 0 0 0 1. So observe that this is the Jordan form for a matrix which has 4 repeated eigenvalues at 1. Right? Because we have 1, 1, then we shift it, and then we get this 1 in the last row. So this is going to be quite possible. So you can just figure out what the eigenvalues are. These are going to be 4 repeated eigenvalues at 1. So let's just check this quickly. And have 1 minus lambda and minus lambda. And this is upper triangular. And then 1, 0, 0, 1, 0. Okay, so this is 1 minus lambda. And then 1 minus lambda. This is 1. Okay, so just a second. 1 minus lambda with the determinant of this matrix. And this is 1. And then minus 1 with the determinant of this matrix. So this goes away, this goes away. So this is 0, 1, 0, 0, 1 minus lambda 1, 0, 0, 1 minus lambda. And 1 minus lambda away. The only term from the this. And then we have this is simply 0. The Jordan form for the matrix or just a Jordan log. Sorry. Jordan log for lambda equals 1. We will generate multiplicity of 4. Alright. So now, so according to the above definition, the matrix A is not selected, right? Because the Jordan form should only have one Jordan block associated with each distinct diagonal. One block is implies that the matrix A is not selected. You can also find this out using the geometric multiplicity approach. We have A minus lambda I or A minus A, sorry, A minus I. This is 0, 0, 0, 0, 0, because it's an upper triangular matrix. And we have 1, 1, 0. So this is 0 and 1. So rank of this is the rank of this matrix. because we are trying to apply the rank nullity theorem to find the dimension of that null space. So you can see that there are three linearly independent rows, row 1, row 2, and row 3. So the rank is therefore 3. Therefore, according to the rank nullity theorem, so n is 4 here. Therefore, the dimension of the null space for lambda equals 1 is 4 minus 3, which is 1. Therefore, Gn is 1. So this is the 0 actually. Numbers. Stop. 0. 0. So only two of the rows are linearly independent. Oh, A is not satisfied. I think our second matrix too. Yes. Let's name this A2. This is -1, -1, 0, 0, -1, 0, 0, 0, -2. So this is simply an upper triangular matrix. You can find out that the eigenvalues are -1, -1, and -2. So A2 is Hurwitz. And for lambda equals -2, algebraic multiplicity is already 1, which implies Gn is also 1. So we have to check geometry multiplicity for lambda equals -1. So for that, let's first find out the rank of A2 plus I. This corresponds to lambda equals -1. So this is 0, 0, -1, -1, 0, or this matrix. So you can easily see that only these two rows are linearly independent. So R1 and R2 are linearly independent. So the rank is 2. And again, according to the rank ID theorem, function of n corresponding to -1 equals 3 minus 2, which is a geometric multiplicity. Therefore, we have that the matrix A2 is cyclic. Alright. Let's move on to the next question. Okay, so consider the LQR system. X2 x dot equals ax plus bu, where we have these following matrices. A equals minus 0.01, minus 0.02. This is a diagonal matrix, so the eigenvalues are simply negative 0.01 and 0.01. So therefore, the matrix A is limitless. And B is 1, 1, minus 0.25, 0.75. Therefore, we have two inputs, where this and u is some the input is a feedback window. So this is u equals some matrix f times x. So therefore, f is going to be a 2 by 2 matrix. Now we have to verify that the three different state feedback matrices. So this is f1 equals minus 1.1, 0, 0. And then there's another feedback matrix. And finally f3. Which is minus 0.1, minus 0.1, 0, 0. Therefore, okay, let's just complete the section. So verify that these three different state feedback matrices, all of them assign the closed loop eigenvalues at the same locations. Point 10.5 plus minus j 0.0544. So this means that f is not unique for a given set of desired eigenvalues. So there can be multiple state feedback matrices which one can use. So that the closed loop system, so that would be A plus BF has same eigenvalues for a given set of desired eigenvalues. Alright, so how do we check this? This is very simple. U is f of x, which implies that x dot is A plus BF times x. So all we have to do is find out the eigenvalues of A plus BF for f1, f2, and f3. So the first one is all the matrix f1. Just a second. So let's substitute the matrices in A plus BF. So A is the diagonal matrix minus 0.01, minus 0.02, 0, 0. Yes, B is 1, 1, minus 0.25, 0.75, 1.1, minus 3.7, 0, 0. This just a diagonal matrix. So, alright, so we have minus 1.1, minus 3.7, and we have, okay, so I'll just calculate this. Zero point eight five, minus 1.1, and then 0.275, and then similarly, then 0.925. So this becomes, this is the same, this is also going to remain the same. So it's 1.11, and then we have 0.03 plus 1.5. Now, so this is simply 0.905. Okay, and now we have to check the eigenvalues of this matrix. We have determinant of A plus A1 minus small I. Plus minus 1.1 minus lambda 0.905 minus lambda 0.7 1 into 0.905 square equals 0. We have lambda square and we have plus 0.205 lambda, and then the constant is 1.0175 and then 10.004. This is plus 0.10129. Alright, so the roots are going to be 190.05. Let's just start. So we have 1.15. Okay, so there might be a mistake somewhere, right? plus minus. We have to just take 0.030. Okay, so it's fine. Plus minus b squared. So we're going to say 5 squared minus 4ac. So we simply have 1 into 0.01 divided by this is by 2. So we have minus 0.1025 plus minus 0.05 by 0.5 considered. So you can check what this comes out to be. Alright. So similarly, we have for F2 and F3 as well. We have to figure out what is A plus B F2. Check the eigenvalues. Question on how to design a straight feedback matrix for the multivariable trees. This is question 6. And by the following matrices. Is 0, 1, 0, 0, 0, 1, 0, 1, minus 1. 0, 1, 1, 1 is 0. Straight feedback matrix. So that the closed loop system. Its eigenvalues at 2, and the other one is a pair of complex conjugate eigenvalues, so it's minus 1 plus minus 3. Right. So for this, you have to first find out if the pair AB is controllable or not. We also discussed it in the last session. That is, to design a state feedback controller, we have to first check whether the pair AB is controllable or not. The controllability measures for this case is B, AB is to AB. Right. So AB is 0, 1, 0, 0, 0, 1, 0 to minus 1, times the matrix. So 0, 1, 1, 1, 0, 0. Okay, so this is simply 1, 1, 1, 0, 0, and we have 2. Then we have a squared b. So this is simply a times ab, 0, 1, 0, b minus 1. 1, 1, 0, 0, 2. First have 0, 0, then 2, 2, and then we have minus 2, minus 2. So this is simply 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 2. Okay, so you can observe this, right? That these two columns are same, that these two rows are same. Okay. 2 plus 1 plus 1. That was 3, so 4 linearly independent columns. Let me just check this. There's going to be the minimum of 3 rows. This is columns, so the rank is going to be less than or equal to 3. So let's just simply check the row instead. So we can just observe that this can be organized. So let's just 1, 2, 3, 4, 5, 6. You see the can be organized C1 plus let's see C3 plus C5. Let's see if this is correct. We have 0, 1, 0 plus 1, 0, 2. And it was 0, 2, minus 2. Yeah, so let's just check the rows instead. This is a good idea. Okay, so we have 3 rows instead of the 6 columns. We have row 1, row 2, row 3. So we have alpha 1, row 1 plus alpha 2, row 3. Plus alpha 3, row 3 is secret. Okay, so let's see. So the first equation is going to give us alpha 2 equals 0. Then we have alpha 1 plus alpha 2 equals 0, which simply means alpha 1 is 0. And the third equation, so what I'm doing is, this is at 1 times alpha 2 times alpha 3 times. So the first equation is multiplying alpha 1, alpha 2, alpha 3 by this column. The second equation is now multiplied by the second column. Similarly, the third equation is alpha 1 plus 2 alpha 3 equals 0. It's alpha 3 is 0. Therefore, rank of the control matrix is 3, which implies that the pair AB is controllable. Take feedback from the matrix. So, let's recall a theorem from this week's lecture. For an n-dimensional system, p-dimensional input, and if the pair AB is controllable, so all of this is satisfied. A is cyclic, so we still have to check this. Then for almost any vector V in R1, a single input pair, ABV is controllable. Okay. So what we're trying to do is transforming the multi-input case to a single input case. Okay. So P equals to, and to determine whether it is cyclic, we have to again look at first of all the eigenvalues of P. This is simply determine of so minus lambda. So for the extra the energies are 0 and this is 0. Simply minus lambda minus lambda minus 1 minus lambda minus 2 equals 0. Okay, so we have lambda equals 0 and lambda squared plus lambda minus 2 equals 0. So we can compute this. We have the eigenvalues 0, minus 1, minus 2. So you can see that AM equals 1 for all lambda, which just implies that GM is also going to be 1. And the matrix A is cyclic. So A is cyclic, the pair AB is controllable. Now we have to find the vector. A and B, this pair is controllable. Okay. So we have to find the value of the vector V. Sorry, this is V. V is going to be some vector that entries V1 and V2. Okay, so we'll choose first. So let's say that V is 1, 1. So PV is therefore, we can check this. So let's see 1, 1, 1, 0, 0. Right to 1, 1. This is 1, 2, 0. Alright, now we have to check the controllability of A and BV. So let's do this. C prime maybe. BV is like to BV on base for AB. Down directly is 1 to C prime is 1 to 0. 2 0 4 0 4 minus 4. its name is C2 instead. Okay, so we check if this is full rank. Let's find out the determinant. So this is 1 by t minus 2 times. Where U is not controllable. So for this choice of V, the pair A times A and B are not controllable. Have to check for some other V. Start with the basic one. So equations will be V. I'm going to write this down directly. V is 0, 1, 0. In this case, the controllability matrix is C3, which comes out to be 0, 1, 0, 1, 0, 2, 0, 2, minus 2. Let's check the determinant of C3 minus 1 minus 2. Okay, so we have found a V such that the pair A, B, V is controllable. Multi-input case into a single input case. And now we have to do the eigenvalue assignment for the pair A and BV. So eigenvalue assignment. So this is going to be A plus, so it's BK. So BK and this is going to be BV times 3. Okay, so this implies that K is going to be some row vector, K1, K2, K3. So I'm going to write this down. That is A plus BV and K looks like. This is 0, 1, 0. K1, K2, K3 plus 1, 0, 1, minus 1. So we'll use this. But first we have to figure out the desired characteristic polynomial. So the desired eigenvalues are at minus 2, 1, minus 1, plus 1 is 2. Okay. We can simplify this. I'm going to write this down. So we expand this. This becomes lambda cube plus 4 lambda squared plus 6 lambda plus 4 equals 0. Okay. And now we have to match it with the characteristic equation of the closed loop system. So then we have characteristic equation of A plus B. So this is simply determinant of A plus B 3 minus lambda r equals 0. Okay, so I'm just going to write this down directly. This is lambda cube minus lambda squared k2 minus 1 minus lambda k2 plus k3 plus 2 plus k1 minus k1 equals 0. So you can check this later. And now on comparing the coefficients, let's say comparing the coefficients of one and two. We get that 4 should be equal to 1 minus K2. Let's simplify that. K2 is 3. K2 is minus 3. Then we have K1 as minus 4. Then finally we have K2, which is minus 3 plus 2K3 plus 2 plus K1, which is minus 4, equals 6. So this is 2K3 minus 5 equals 6. K3 is 11 by 2. Let me just check. Yeah, let's just keep it like this. So the K vector becomes minus 4 minus 3 minus 1 plus 3 5.5. Now let me check if you're getting the coefficients. Okay. This was actually minus of 6.5. Okay. Okay. Then K2 is going to be body K. So for example, it's K2, which is going to be B times K1. So this is going to be 1, 0 means K1, which we can write as last minus 4 minus 3 minus 0.5 1 zeros. And then again we'll find out characteristic equation of K plus B times K2. So I'm going to write this down. So we get lambda 2 just a second. We get lambda 2 plus 4 lambda square plus 6 lambda plus 4 equals 0. This was the desired one. And you can compare the coefficients to find out whether A plus BJ2 has the same eigenvalues or not. So these are the same because we have designed B such that where A, B is controllable and then it will be the coefficients for one and two. There is another method which was discussed. Method. So we know that the eigenvalues of A are at of A are 0, minus 1, minus 2. And the desired eigenvalues are minus 2, minus 1, plus minus 0. So these are already the same. So we have to transfer 0 and -1 to this complex contributor. It's capital F. So let's recall the theorem. So recall that if A and F have no eigenvalues in common, then the unique solution of the unique solution given by P of the diagonal equation Bt minus T equals Bt bar is non-singular. Each one of is the pairs AB and F transpose T bar transpose are controllable. Generally, K bar is the matrix of size P by N, and therefore for our case, K bar is the matrix of size 2 by 3. So let's choose this arbitrarily. This is, for example, 1, 2, 0, 0, 0. Chosen arbitrary. Okay, and now we have to choose F. So, this is simple. And how do we choose F? We have to choose F such that it doesn't have any eigenvalue in common with A, and the pair F transpose K bar transpose is controllable. So the controllability matrix for the system is going to be K bar transpose, F transpose, K bar transpose, F transpose square, K bar transpose. Just one second. So first of all, let's choose F. It doesn't have any common eigenvalue with A. So this is -3. So the easiest way to choose F is to choose a diagonal element so that we know what the eigenvalues are, and we just keep them different from the eigenvalues of A. So in this case, we are saying that we have repeated eigenvalues, so -2 something like this. So this is from, let's say, some lambda, and then let's say some complex conjugate pair. So for that, alpha plus minus j beta. The block looks like alpha plus beta minus beta and alpha. So one of the eigenvalues is at -3, and the complex conjugate pair is at -1 plus minus j. So you can notice that this is also the desired eigenvalue. One of the pair of desired eigenvalue lambda b. Okay. Now let's the controllability matrix for the pair F transpose and K bar. K bar transpose. I'm going to write this down directly. This is 1, 0, 0, -3, 0, 9, 0, and 2, 1, 1, -2, -1, 0, 0. So you can check if the three rows are linearly independent or not. So we'll check this later. I'm going to write this down that rank is 3. Therefore, the pair F transpose, the bar transpose is controller. Okay, so F satisfies both the conditions. And now we have to find the solution to the Lagrange equation. So that is AT minus TF. T is going to be a 3 by 3 matrix. Say P1, P2, P3, 4, 5, 6. You can substitute in this equation and find out what T should be. So once you have T, so calculate how T is. And once you have T, the gain matrix K is simply K bar times K inverse. So this is such that A minus PK has desired eigenvalues. Alright. So now let's do the last question. Okay, so consider the LQR system defined as y double dot equals v. So we will use the word y in your. There y is the output. And u is the input. So we have to determine its p to minimize the following cost. Minimize the following cost. The cost is 0 to infinity. This is the running cost. Yt square of output plus square of input minus dv. Okay, so first let's transform this into a standard LTI system or state space system. Y double dot equals u. Let's say that this is a second order differential equation. So we have two states. Let the first state be the input and the second state is therefore going to be x1 dot, which is y dot. Okay, so we have that x1 dot equals x2 and x2 dot equals the input. So we have x1 dot, x2 dot equals 0, 1, 0, 0, x1, x2 by 0, 1 times u. Y is simply the first state. So 1, 0, x1, x2. So now we have the system in the standard ATF form. So in this case, what does the cost J look like? It is simply x1 square t plus u square dt. Okay, so let's recall equations from the LQR setup. So the cost function for LQR is 0 to infinity y transpose q y plus u transpose r u dt. The R case we simply have, so we just have one output and one input. We have q as a scalar 1 R as a stable path. And then we have the algebraic Descartes equation, ARE, which is A transpose P plus PA plus C transpose QC minus PP R inverse A transpose P equals C. So the objective is to find P. So P is going to be 2 by 2 matrix. So, and it's going to be symmetric. So we have P1, P2, and this is going to be P2 again, P3. Okay, so let's compute each of the terms of the algebraic Descartes equation. Formula. So C transpose QC is already known. C transpose C, right? Because Q is 1. Okay. And then we can figure out the rest of the terms of the algebraic Descartes equation and get the values for P1, P2, and P3. So I'm going to write down the matrix form of the equation that we get. So we get 1 minus P2 square, P1 minus P2, P3. So we have 3 equations and 3 unknowns. So we have 1 minus P2 square equals 0, which implies that P2 can be plus minus 1. Which implies that P3 squared is 3P2. So therefore P2 cannot be negative. This is simply 2. P3 can be plus minus under root 2. And then we have the last equation, P1 minus P2 equals 3 equals 0. We have to find out the matrix P, which is already symmetric, but P should be positive dominant. Let's say P equals P1, P2, P2, P3. We have 2 choices for P1 and 2 choices for P3. So it's always symmetric. Let's say that for P1, P3 minus root 2, P becomes minus root 2, 1, 1. And we can either check the eigenvalues of P or find out whether P is positive definite or not using this kind of form. So where X is some general vector, X minus 2. So let's just compute the eigenvalues in this case. We can compute this and we get under root 2 plus minus 1. Are always greater than 0, therefore P is positive definite. P is infinite. P equals Q transpose. Check root 1. So we have found a P cost function. Okay. So before we move on to the next question, recall that given the algebraic Descartes equation, the matrix A minus B R inverse B transpose P is a stability or a Herbert's matrix. find the feedback gain u, which minimizes the cost. So to find u equals minus kx, or to find k is simply R inverse P transpose P. So that's also why we have to find the positive definite and symmetric matrix P by solving the algebraic Riccati equation. Okay, so we have the last question for today then. So consider the system. X1 dot equals x2 and x2 dot equals minus x1 plus. So the objective is to obtain the feedback control T, which minimizes the cost, which minimizes J as a function of U, 0 to infinity, x1 squared plus 2x1 x2 plus x2 squared plus 2u squared. All of these are functions of time dt. Okay, so we can just simply write the state space form. This is 0, 1, minus 1, 0, x1, x2 plus 0, 1, u. And in this case, y is, so we can actually choose this. So this is both the states x1 and x2. Right. So to match the standard form, we need u transpose u. Sorry, u transpose r u. So this implies that r is 4. And similarly, find y transpose q by y1 squared plus y2 squared. Therefore, q should look like something like u1, u2, u3, u4. Because we have x1 squared plus x2 squared. Okay. Then we have the unknown P matrix, which is substitute this in the algebraic Riccati equation. So I'm going to write down the equation directly. So this is, you can check this later. Minus 2p2 plus p1 minus 1 by 4 p2 squared minus p3 plus p1 minus 1 by 4 p2 p3 2p2 plus 1 minus 1 by 4 p2 squared. And then this should be the zero matrix. And you can find out what P1, P2, P3, and these are. So I'm going to write this down. Find these. Solving the equation. And if there are combinations of these values, find just one P which is positive definite. Okay. And we also have to find and such that the matrix is a stability matrix. So this A minus B R inverse B transpose P is limits. Okay. And then K is simply R inverse B transpose P. So R inverse is simply 1 by 4, and then B transpose is 1 times the value, the matrix P you get. Then the closed loop system is A minus LKX. Okay, just check if this is reverse or not. So this would be the input U equals minus KX, which would minimize the cost. Alright, so that's it for today. I hope that the questions were clear to you. Okay, so let's end for now. Thank you.